There is a place in the universe that should not be cold. It is a dying star, 5,000 light-years away, caught in the act of tearing itself apart. It is a cloud of gas expanding at 164 kilometers per second. It is, by every known law of physics, a place that should be hot. It is not. It is the coldest natural object ever found. It is so cold that it absorbs the warmth of the Big Bang itself. It drinks the afterglow of creation and gives nothing back. And that should not be possible. Because the universe has a temperature it is supposed to have, it is written into every direction we look. A faint, even glow, 2.725 degrees above absolute zero. The same temperature behind the stars of the north as behind the stars of the south. Turn a sensitive enough antenna toward any patch of empty sky, any patch at all, and you will hear it. A quiet hiss. A warmth that has no source you can point to, because its source is everywhere at once. This is the afterglow of creation. The light left over from the beginning of everything, cooled and stretched across 13.8 billion years until it became this gentle whisper. And it is difficult to overstate how universal it is. There is no corner of the cosmos that escapes it. Travel to the most remote void you can imagine, a place so far from any galaxy that the nearest star is too distant to see, where there is nothing in any direction but emptiness stretching for billions upon billions of miles. And even there, the glow persists. It is the one thing that is truly everywhere, the single feature shared by every point in the entire universe. It is the closest thing the cosmos has to a single shared temperature, a thread of sameness running through all the vast and varied dark. This is the floor, the minimum, the coldest that empty space is allowed to be. And this one dying star slipped beneath it, not by a little, not by some technicality of measurement that a careful scientist might explain away. In the southern constellation of Centaurus, a cloud of gas and dust does what nothing in the open universe is supposed to do. It does not merely sit in the cold. It absorbs the cold. Against the gentle, even glow that fills all of space, this one object appears as a shadow, a pocket of something deeper, a place where the thermostat of the cosmos was somehow impossibly turned down lower than its lowest setting. To picture it, imagine standing in a vast, dim room, lit evenly everywhere by a soft and uniform glow, so that there are no shadows anywhere, no darker corners, just the same gentle light in every direction. And then imagine that in one place, against that even glow, there appears a patch that is darker than the light around it. Not because something is blocking the light, but because that patch is somehow drinking the light in, absorbing the very glow that fills the room, casting a shadow not by obstruction but by sheer cold. That is what the Boomerang Nebula does against the background of the universe. It is a dark patch in an evenly lit cosmos, a place colder than the light that bathes it, swallowing the ancient glow and giving nothing back. By every reasonable expectation, it should not exist. And yet there it is. We have measured it. We have photographed it. We have watched it for more than 40 years. It is real. It is out there. And tonight, slowly and without any hurry at all, we are going to try to understand it. So settle in, get comfortable. Let your breathing slow. We are going to travel 5,000 light years to find the coldest place that has ever been found. And then we are going to ask the question that has no comfortable answer. How is anything colder than space itself? The story does not begin with a revelation. It begins the way so many of these stories do, with something small and strange that nobody quite knew what to do with. The year was 1979. Two astronomers, Keith Taylor and Mike Scarrett were studying the southern sky. They came across an object that was faint and unusual. It had a peculiar shape, two soft lobes of light leaning away from a central point, like a bow tie, or like the gentle curve of a boomerang lying against the dark. They gave it a name that described what they saw, the Boomerang Nebula. At the time, it was just another curiosity. The sky is full of them. The light coming from this object was strange in a way they could measure but not fully explain. It was highly polarized, which is to say the light waves were unusually organized, all leaning in similar directions, the way light behaves when it has bounced off dust rather than shining directly toward you. The shape was lopsided and delicate. It did not match the neat categories astronomers like to sort things into. So it was noted, it was catalogued, and then, for the most part, it was set aside. A small mystery filed away among thousands of small mysteries, waiting for someone to come back to it with better tools and a sharper question. That someone arrived 15 years later. In 1995, two astronomers named Raghvendra Sahai and Lars Ake Niemann turned a powerful instrument toward the Boomerang Nebula. The instrument was the Swedish ESO submillimeter telescope, perched high in the dry mountain air of Chile, built to detect a kind of light that human eyes cannot see. Not visible light, but radiation with much longer waves, the kind given off and absorbed by cold molecular gas drifting in space. There is a quiet lesson in that 15-year gap, and it is worth pausing on. The Boomerang Nebula was discovered, named and catalogued long before anyone understood what it truly was. For a decade and a half, it sat in the records as a minor curiosity. Its great secret, entirely unsuspected, waiting. This is how a great deal of science actually unfolds, far from the dramatic image of sudden breakthroughs. The crucial object is often already known, already sitting in some catalogue, already photographed and filed away. What changes is not the object, but our ability to question it. Better instruments arrive. Sharper questions get asked. And something that had been hiding in plain sight for years suddenly gives up its secret. The coldest place in the universe had been sitting in the astronomical record for 15 years before anyone realized it was extraordinary. It was not hiding in some unexplored corner of the sky. It was already on the list. We simply had not yet learned how to see what it was. They were not looking for anything dramatic. They were looking for carbon monoxide. This is routine work in its way. Carbon monoxide is one of the most useful molecules in all of astronomy. Not because it is rare, but because it is reliable. It is everywhere that cold gas gathers, and it announces itself clearly in exactly the kind of light this telescope was built to catch. Find the carbon monoxide, and you can map the gas. Measure how its light is shifted and shaped, and you can learn how that gas is moving, how dense it is, and how warm it is. So they pointed the telescope and they listened for the familiar signal of carbon monoxide around this strange little nebula. What they found was not a glow, it was a shadow. The carbon monoxide molecules around the Boomerang Nebula were not emitting light against the darkness of space. They were absorbing it. They were sitting in front of the faint background radiation that fills the universe, the afterglow of the Big Bang, and they were drinking it in, blocking it, casting a cold shadow against the oldest light there is. And this is the moment where a routine measurement became something else entirely. Because there is only one way for a cloud of gas to absorb that background radiation instead of glowing against it. The gas has to be colder than the radiation itself, colder than the background of the universe, colder than 2.725 degrees above absolute zero. Let that settle for a moment, because it is the whole heart of the story, and everything else we say tonight grows out of it. The afterglow of the Big Bang is the gentlest warmth imaginable. It is barely a breath above the coldest temperature that can exist. For 13.8 billion years, it has been the one temperature you could count on finding anywhere, the baseline that everything in the universe is bathed in. To be colder than that background, an object cannot simply be cold. It has to be doing something. It has to be actively pulling itself beneath a floor that the universe laid down at the dawn of time. When Sahai and Nyman worked out the numbers, the answer came back almost too extreme to believe. The gas in the Boomerang Nebula was sitting at roughly 1 degree above absolute zero, 1 Kelvin. In the units you might use on a cold winter morning, that is about minus 272 degrees Celsius, minus 458 degrees Fahrenheit. It is colder than the dark side of the most distant, sunless world, colder than the empty space between the stars, colder than the empty space between entire galaxies where there is nothing at all for billions upon billions of miles. The Boomerang Nebula is colder than all of it. Colder, as far as we have ever been able to measure, than any other natural object in the known universe. It holds a record that sounds almost like a contradiction. The coldest place we have ever found is not in the deepest, emptiest void between galaxies, where you might reasonably expect to find it. It is wrapped around a dying star. Now, it is worth pausing to appreciate how strange it was, even for the astronomers themselves, to arrive at this conclusion. Because when you find a measurement this extreme, your first instinct, if you are a careful scientist, is not to believe it. Your first instinct is to doubt it, to assume you have made a mistake. Extraordinary claims, as the saying goes, require extraordinary evidence, and there are few claims more extraordinary than the discovery of a place colder than the universe itself. So the measurement had to be examined and re-examined. The reasoning had to be followed carefully, step by careful step. And the reasoning, in the end, was difficult to escape. It went something like this. The carbon monoxide gas around the Boomerang Nebula was absorbing the background radiation. This was directly observed. It was not an inference or a guess. It was there in the data, a shadow cast against the ancient light. And there is no way for gas to absorb that background radiation unless the gas is colder than the radiation. Warmer gas would glow against the background, adding light. Only colder gas absorbs it, subtracting light, casting a shadow. The shadow was there. Therefore the gas was colder than the background. Therefore the gas was colder than the universe's floor. The logic was simple, almost brutally so, and it led to a conclusion that should have been impossible. And the temperature it pointed to was so low that it strained belief. To understand just how low, it helps to climb down the scale of cold, step by step, and feel how far below everything familiar this number truly is. Consider the coldest things you know. A winter's day might reach a few tens of degrees below freezing. The coldest natural temperature ever recorded on the surface of the Earth, in the heart of Antarctica, was around minus 89 degrees Celsius. That is brutally, lethally cold, cold beyond ordinary human experience. But on the scale we are climbing down, it is barely the first rung. Keep going. The surface of a sunless, frozen world far from any star sits far lower still, down past minus 200 degrees, where the very air of our own planet would freeze solid and fall as snow. Lower than that lies the temperature of the empty space between the stars, the cold of the open void, settling toward the universal background that fills all the dark. That background is the bottom of the familiar scale, 2.725 degrees above absolute zero. The cold that everyone, knowingly or not, has always assumed was as low as the open universe could go. It is the floor we have been describing, the baseline laid down at the dawn of time, and the Boomerang Nebula sits beneath it. It has stepped off the bottom rung of a ladder that was supposed to have no rung below it. The astronomers who found it had to sit with that, had to check it and recheck it, before they could allow themselves to believe what their own instruments were telling them. But the data held. The shadow against the ancient light was real, and so the impossible conclusion stood. There was, against every reasonable expectation, a place colder than the universe, and it was wrapped around the corpse of a dying star. Take a breath here, because the discovery is only the beginning. The discovery is the easy part. Strange as it is, a measurement is just a number. The hard part, the part that has occupied astronomers for decades, is the question that comes immediately after. How is this possible? Not in some vague hand-waving sense, but mechanically, physically, step by step. How does a cloud of gas around a dying star become colder than the background of the entire cosmos? To feel the weight of the problem, you have to understand why it is a problem at all. And to understand that, it helps to think about something much closer to home. The refrigerator humming quietly in your kitchen. A refrigerator is, when you think about it, a small miracle of physics. The inside of it is colder than the room around it. That should strike you as slightly strange, because heat naturally flows from warm to cold, not the other way around. Left to itself, the warmth of your kitchen would seep into the fridge and even everything out. To keep the inside colder than the outside, the refrigerator has to fight against the natural direction of things. It has to actively move heat from the cold inside to the warm outside, uphill, against the current. And to do that, it needs two things. It needs a mechanism, a compressor that squeezes and releases gas in a careful cycle. And it needs energy. It needs to be plugged into the wall. Pull the plug, and the magic stops. The compressor falls silent, the warmth creeps in, and within a day your refrigerator is simply a box at room temperature like everything else. There is one more thing to understand about your refrigerator. Even working perfectly, plugged in, running forever, it can only get so cold. It can chill your food to a few degrees above freezing, but it cannot reach the temperature of an Antarctic winter, let alone the temperature of deep space. To go colder, you need better machines, more powerful mechanisms, more energy poured in. The colder you want to go, the harder it gets, and the more you have to spend to get there. This is not a small detail. It is one of the deepest truths about cold, and it is worth dwelling on, because it runs against our intuition. We tend to think of cold as simply the absence of heat, as nothing at all, as what you have left over when the warmth is gone, and in a sense that is true. But producing cold, real cold, deep cold, is not a matter of doing nothing. It is a matter of doing a great deal of work. Heat flows toward cold naturally, all on its own, the way water flows downhill. But to make something colder than its surroundings, to push heat the other way, uphill, against its natural direction, requires effort and energy and clever machinery. The deeper the cold, the greater the effort. Approaching the lowest temperatures is one of the hardest things to do in all of physics, and it gets exponentially harder the closer you try to get to the bottom. So when we say the Boomerang Nebula is colder than the universe, we are not describing a place where nothing is happening. We are describing a place where something remarkable is happening. A place where cold is being actively produced on an enormous scale, against the natural flow of heat, without any of the machinery we would normally think such a feat requires. Now hold that picture in your mind and look back out at the Boomerang Nebula. It has reached, in the open dark of space, a temperature so low that here on Earth it requires some of the most sophisticated and delicate machinery human beings have ever built. Machinery worthy of Nobel Prizes just to approach. Everything we understand about producing cold says this should take enormous effort, and intricate apparatus. The deeper you go, the harder it becomes, the more elaborate the machine required. To reach a single degree above absolute zero is, by every rule we know, a monumental undertaking. And it has no compressor, it has no power cord. There is no machine out there in the dark carefully cycling gas to pump heat away. There is only a dying star. And here is what makes that so deeply strange. A dying star is not a refrigerator. A dying star is, if anything, the opposite. It is one of the warmest, most violent objects in nature. It is a furnace running low on fuel, swollen and unstable, shedding its outer layers into space. When a star reaches the end of its life, the expectation is heat, glowing gas, radiation pouring outward, the slow, bright funeral of something that burned for billions of years. The Boomerang Nebula turns that expectation completely on its head. At the center of the coldest known place in the universe sits a star in the act of dying. And somehow, against everything we would predict, the death of that star is producing not warmth, but the deepest cold ever recorded. So, something is happening here that we did not expect a dying star to be capable of. Some mechanism, some hidden source of refrigeration tucked into the physics of a star's final moments. And whatever it is powerful enough to do what no machine we have ever built could do unaided in the open dark. It is a process we will have to uncover piece by piece, because nothing about a dying star, as we usually understand one, prepares us for it. The universe has built a freezer with no power cord, set it colder than the cosmos itself, and done it using nothing but the violence of an ordinary star's undoing. Before we go looking for how, let us get a sense of the thing itself, the basic shape of it, the dimensions of the mystery. The Boomerang Nebula sits about 5,000 light-years away from us, in the direction of the constellation Centaurus. 5,000 light-years is a distance that the human mind cannot really hold. The light you would see from it tonight, if your eyes were sensitive enough, left that nebula 5,000 years ago. It departed when the first cities on Earth were young, when the great pyramids had not yet been built, and it has been traveling across the dark every moment since, only now arriving. The nebula itself is roughly a light year across. That is to say, light, the fastest thing there is, would take about a year to cross from one side of it to the other. It is a vast, tenuous cloud, far larger than our entire solar system, far larger than the distance to the nearest star beyond our own. It is worth dwelling on that distance of 5,000 light-years for a moment, because numbers like these wash over us so easily, and they deserve better than that. A light-year is the distance light travels in a single year, and light is fast, almost beyond comprehension. In 1 second, a beam of light could circle the Earth more than 7 times. It crosses the entire span from the Sun to the Earth, 93 million miles, in about 8 minutes. At that staggering pace, light travels nearly 6 trillion miles in a single year, and the Boomerang Nebula is 5,000 of those light-years away. So the light you might gather from it tonight is genuinely ancient. It left the nebula 5,000 years ago and has been racing toward us 6 trillion miles every year without rest ever since. When that light began its journey, the wheel had only recently been invented. Writing was new. The great civilizations of antiquity were just beginning to stir. Every empire that has ever risen and fallen, every word ever written down, every life of every person who has ever lived in recorded history, all of it has happened in the time it took that light to cross the gulf between the Boomerang Nebula and your eyes. To look at it is, in the most literal sense, to look into the deep past. We never see the nebula as it is now. We see only the light it sent out long ago, a message from across an ocean of space and time, arriving at last. And it is expanding. The gas is flowing outward from the central star, away in all directions, and it is doing so at a tremendous speed, about 164 kilometers every second, 100 miles, give or take, in the time it takes to say the word. Hold on to that number, because it is the first real clue. 164 kilometers per second is not a normal speed for the gas flowing off a dying star. It is not even close. A typical dying star sheds its outer layers gently, almost reluctantly, at speeds of perhaps 10 or 20 kilometers per second. The Boomerang Nebula is pushing its gas outward roughly 10 times faster than that. Something gave this gas an enormous shove. Something flung the outer layers of this star away with a violence that ordinary stellar death cannot explain. And as we will see, that violence, that tremendous speed, is not separate from the cold. The speed is the secret. The speed is how a dying star became the coldest place in the universe. But to understand why, we first have to leave the Boomerang Nebula behind for a little while. We have to pull back and up and out and look at the wider story of how stars die. Because the cold at the center of this tale only makes sense once you understand the ordinary, beautiful, violent process that every star like our own is fated to undergo. So let the nebula shrink behind us. Let it become one cold point of light among the millions, and let us turn for a time to the deaths of stars. Every star is living on borrowed time, ours included. A star is a balance. It is a war that holds itself to a perfect, quiet stalemate for billions of years. On one side, there is gravity, the relentless inward pull of all that mass trying to crush the star down into nothing. On the other side, there is the outward push of energy from the fusion burning in the core, where hydrogen is being squeezed and fused into helium, releasing the light and heat that we feel from 93 million miles away. Inward pull, outward push, held in balance. For most of a star's life, these two forces are matched so evenly that the star barely changes at all. It simply shines, steady and patient, for an almost unimaginable stretch of time. Our own sun has been holding this balance for about 4.5 billion years. It will hold it for roughly 5 billion more. This long, stable middle age is what astronomers call the main sequence, and it is where stars spend the overwhelming majority of their existence. It is the calm, the plateau, the long, bright afternoon of a star's life. There is something steadying in that thought, something almost reassuring when you sit with it in the quiet. The sun that warms your days, that has risen over every morning of every life that has ever been lived, is in no hurry. It is halfway, roughly, through a life that spans 10 billion years. It was already ancient beyond reckoning when the first single-celled life stirred in Earth's oceans. It will still be shining, steady and warm, long after everything we have ever built has crumbled to dust and been forgotten. On the scale of a human life, on the scale of all of human history, the sun is the very image of permanence. It simply shines and shines and shines, but it cannot last. No fuel is infinite, not even the fuel of a star. Deep in the core, the hydrogen is slowly running out. For billions of years, the star has been fusing hydrogen into helium, and the helium has been collecting at the center like ash at the bottom of a fire. And then, eventually, the core has burned through the hydrogen it can reach. The fire at the very heart of the star begins to falter. When that happens, the long balance breaks. With the fusion in the core sputtering, the outward push weakens, and gravity, which has been waiting patiently for billions of years, finally begins to win. The core starts to contract, squeezing inward, growing hotter and denser as it shrinks. And here the story takes a turn that feels almost backward, almost paradoxical, but is one of the most beautiful facts in all of stellar physics. As the core contracts and heats, it pours fresh energy into the layers of hydrogen still surrounding it. That shell of hydrogen, wrapped around the shrinking core, ignites. And this new burning, this shell of fire around the dying center, releases so much energy that it pushes the outer layers of the star outward. The star does not shrink as it dies, it swells. It swells enormously. A star like our sun will balloon outward until it is dozens, even hundreds of times its original size. Its surface, now stretched across an immense new volume, cools and reddens. It becomes a red giant, a vast, bloated, glowing thing, cooler at its surface than it once was, but far larger and far brighter overall. The transformation is staggering to picture. Take our own sun, that familiar disk in the daytime sky, and imagine it swelling until it swallows the orbit of Mercury, then the orbit of Venus, reaching outward toward the orbit of the Earth itself. A star that was once a modest point of fire becomes a monstrous, distended sphere, its outer surface so far from its core and so thinly spread that it glows a sullen red rather than brilliant white. The density of those outer layers becomes astonishingly low, thinner than what we would call a vacuum in a laboratory on Earth, and yet the sheer volume of the thing makes it shine with the light of thousands of ordinary stars. It is a strange and contradictory object, the red giant. Enormous, yet tenuous. Brilliant, yet cool at the surface, swollen with the energy of its own dying, and loosely holding outer layers that it is already beginning to lose. When our own sun reaches this stage, billions of years from now, it will swell so large that it may swallow the inner planets entirely. Mercury, gone. Venus, gone. The Earth, scorched, perhaps consumed, certainly rendered into a barren and lifeless cinder long before the end. The red giant phase is the beginning of the end for any sun-like star, and it is a phase of tremendous, restless instability. Because a red giant is not a calm thing. Its outer layers are held only weakly now, draped loosely across an enormous volume, far from the gravitational grip of the core. The star begins to pulse. It throbs, expanding and contracting in slow, mighty heartbeats, each one loosening its hold on its own outer atmosphere a little more. And with each pulse, with each shudder, the star sheds some of itself into space. It begins to lose mass, casting its outer layers off into the dark, like a fire throwing sparks that never come back. These pulsations are not gentle. In the late stages, a dying star of this kind can undergo great, rhythmic convulsions, swelling and shrinking over months and years, growing brighter and dimmer as it heaves. Each cycle drives more of the loosely held outer material outward, building up great shells and clouds of expelled gas around the star. Over time, the star quite literally takes itself apart, layer by layer, casting its own substance into the surrounding space until the once mighty giant has shed much of its mass and only the dense inner core remains. The matter that drifts away on these pulsing winds carries with it the elements forged in the star's long life, the carbon and oxygen and other ingredients cooked up in the stellar furnace, scattering them into the galaxy where they may one day gather into new stars, new worlds, perhaps even new life. The death of a star is also a kind of seeding. What the dying star throws away becomes the raw material of whatever comes next. This is how stars like our sun end. Not in a single dramatic explosion, but in a long, gradual unraveling. a slow exhalation of their own outer cells into the surrounding void, until little is left but the exposed, cooling core. But between the red giant and the final quiet, there is one more phase, a brief and violent transition. And it is in this fleeting moment that the Boomerang Nebula is frozen. After the red giant has shed enough of its outer layers, something changes. The exposed inner regions of the star, the contracting core, begin to grow very hot. But for a short window of time, the core is not yet hot enough to do what it will eventually do, which is to flood the surrounding gas with intense ultraviolet light and set it glowing. There is a gap, an in-between. The star has thrown off its outer envelope, but it has not yet lit that envelope up. Astronomers call this stage the pre-planetary nebula. It is the chrysalis stage of a dying star, the cocoon between the caterpillar and the moth. The old outer layers have been cast away and are drifting outward into space, expanding, cooling, but the central star has not yet become hot enough to make them shine. So for a brief time, the ejected gas simply drifts in the dark, cold and unlit, a shroud of expelled material expanding around a star that has not yet found its final voice. And here is the crucial thing. This phase does not last long. Not by the standards of the cosmos. A star spends billions of years on the main sequence. It spends many millions of years as a red giant. But the pre-planetary nebula phase lasts only a few thousand years. A cosmic eye blink, a single held breath in a life that spans the age of the universe. To catch a star in this exact moment, to find one in the brief flicker of the pre-planetary phase, is a piece of genuine fortune. And the Boomerang Nebula is caught precisely here. It is a star frozen in the act of its own transformation, in the narrow window between throwing off its outer self and lighting that self ablaze. It is a star caught dying. And in the particular way that this star is dying, in the violence and the speed of its unraveling, lies the answer to the great cold at its heart. So let us return now to the Boomerang Nebula, and let us look closely at the star at its center. Because if we are searching for the source of impossible cold, the central star is the obvious first suspect. Perhaps the star itself is somehow strange. Perhaps it is unusually cold, and the chill of the nebula is simply the chill of the star that made it. It is a reasonable thought, and it is wrong, but it is wrong in a way that teaches us something important, so it is worth following. When astronomers study the central star of the Boomerang Nebula, they estimate its surface temperature at somewhere around 6,000 to 7,000 degrees. That is hot. It is, in fact, roughly comparable to the surface of our own sun, which sits at about 5,500 degrees. The dying star, at the heart of the coldest place in the universe, is not a cold star at all. It is a perfectly ordinary, fairly warm, sun-like star going through the late stages of its life. This is the first surprise, and it is a profound one. The cold of the nebula cannot be blamed on a cold star, because the star is not cold. We have a warm star at the center, 6,000 or 7,000 degrees at its surface, and yet wrapped around it is gas that has fallen to a single degree above absolute zero. The star is thousands of degrees hot. The gas around it is colder than the universe. And there is no contradiction in that, only because the cold is not coming from the temperature of the star. The cold is coming from something the star is doing. So let us look at what the star is doing. And here, the numbers become genuinely extreme. The first thing to notice is how much mass the star is losing. Dying stars all shed mass, as we have seen. But the central star of the Boomerang Nebula is shedding mass at a tremendous rate. casting off its outer layers far more aggressively than a typical dying star of its kind. It is unraveling quickly, throwing material into space in great quantities. But the truly anomalous number, the one that breaks the pattern, is the speed. We met this number earlier when we first surveyed the nebula. The gas is flowing outward at roughly 164 kilometers per second, something like 10 times faster than the gentle winds of an ordinary dying star. At the time, it was simply a striking fact, a clue set aside for later. Now we can see why it matters so much. That speed is not a mere curiosity of this one object. It is the very thing that makes the cold possible, and it is the thing that no ordinary stellar death can account for. Sit with the strangeness of it. A typical aging giant lets its outer layers drift away almost reluctantly, a slow and gentle exhalation into space. This star did not exhale. It heaved. It flung its outer self outward with a violence that the quiet, steady process of single-star death simply does not contain. The gas of the Boomerang Nebula did not leak away. It was thrown hard, and the force of that throw is written into every kilometer per second of its outward rush. This is not a soft exhalation. This is a violent expulsion. Something flung the outer layers of this star away with a force that ordinary stellar death simply does not provide. The gas was not drifting away. It was hurled. And now we arrive at the physical heart of the entire mystery, the connection between that violent speed and the impossible cold. The principle has a name, and the name is adiabatic expansion. It sounds technical, but the idea behind it is something you have felt with your own hands, and once you see it, the whole mystery begins to come apart in the most satisfying way. Here is the principle. When a gas expands, when it spreads out into a larger volume, it cools. And if it expands quickly enough, without time to draw warmth back in from its surroundings, it cools dramatically. You have felt this. If you have ever used an aerosol can, a can of spray paint or compressed air, you may have noticed that the can grows cold in your hand as you use it. That is adiabatic cooling. The compressed gas inside, suddenly released and allowed to expand into the open air, cools as it spreads. The faster and the more freely a gas expands, the more it cools. There are other places this same principle reveals itself, once you know to look. Think of a warm, moist mass of air rising over a mountain range. As it climbs, the air pressure around it drops, and so the air expands, and as it expands it cools, and as it cools the moisture within it condenses into clouds and falls as rain. The clouds that gather around mountain peaks are, in part, a visible signature of adiabatic cooling, gas expanding and chilling as it rises into thinner air. Or think of the way a deep breath blown slowly across your open palm feels cool, while the same breath blown sharply through pursed lips feels cooler still, the air expanding as it escapes the narrow opening. The principle is woven into the ordinary world all around us. Expansion is cooling. To let a gas spread out is to drain the warmth from it. This is in fact exactly the same principle your refrigerator uses. The compressor squeezes a gas and then allows it to expand, and in expanding it cools, and that coldness is what chills your food. Expansion is refrigeration. To expand a gas is to cool it. Now, think about the Boomerang Nebula in this light. Here is a gas being flung outward from a star at 164 kilometers per second. It is expanding into the surrounding emptiness extraordinarily fast, racing outward into an enormous volume of space. And as it expands, it cools, exactly as the physics demands. The faster the expansion, the deeper the cooling. The star, in throwing its outer layers away with such tremendous violence, has built itself a refrigerator out of nothing but motion. The expansion is the compressor. The speed is the power. And the result is a cloud of gas chilled by its own headlong rush into the dark to below the temperature of the universe. So that is the mechanism. The cold is the cold of rapid expansion. The same physics as the chill of an aerosol can or the inside of your freezer, scaled up to the depth of a star and the size of a solar system many times over. But this only deepens the central question, rather than answering it, because we have explained how the cold is produced. We have not explained the thing that produces it. We have not explained the speed. What flung this gas outward at 10 times the normal rate? What gave this dying star the violence to refrigerate a region of space larger than our entire solar system, to push it below the floor that the universe laid down at the beginning of time? A single, ordinary, sun-like star should not be able to do this. The energy is too great, the speed is too high. Something more is going on at the center of the Boomerang Nebula than the simple, lonely death of one star. And in the year 2017, with the most powerful instrument of its kind ever built, astronomers finally began to see what that something was. The Boomerang Nebula, it turned out, was not the death of one star at all. It was the death of two. In 2017, Raghvendra Sahai, one of the same astronomers who had first measured the impossible cold decades earlier, returned to the Boomerang Nebula. But this time, he brought with him an instrument that did not exist when the mystery began, an instrument called ALMA. We will speak more about ALMA soon, about what it is and how it sees. For now, it is enough to know that ALMA is an array of telescopes high in the Chilean desert, working together to see the cold molecular gas of the cosmos with a sharpness and clarity that nothing before it could approach. When Sahai's team turned this extraordinary eye upon the Boomerang Nebula, they were able to study its structure and its motion in detail that had never before been possible. And the picture that emerged offered an answer to the great question of the speed, an answer with a quiet drama all its own. The leading explanation, the one that best fits what we see, is that the Boomerang Nebula was not formed by a single dying star casting off its layers in the ordinary way. It was formed by two stars, and by the violent end of the relationship between them. Imagine the system as it was, long ago, before the catastrophe. A larger star, the primary, a sun-like star aging toward its end, and orbiting it, a smaller companion star, a lesser body bound to the larger one. The two of them circling each other across the ages as binary stars so often do. Most of the stars in our galaxy, in fact, are not solitary the way our own sun is. They come in pairs, or in larger families, bound together by gravity. A binary system is one of the most common arrangements in the cosmos. For a long time, the two stars of the Boomerang system orbited each other in stability. But then the larger star began to die. It entered the red giant phase. It swelled, as dying stars do, ballooning outward to many times its former size. And it swelled so far that it reached its companion. This is the heart of the catastrophe. The dying giant expanded until its own bloated outer layers engulfed the smaller star entirely. The companion, which had been orbiting safely at a distance, now found itself plunged inside the outer envelope of the giant, swallowed by the very atmosphere of the star it circled. What happens next is a process astronomers call common envelope evolution, and it is one of the most violent and dramatic episodes in all of stellar physics. The smaller star, now orbiting inside the gas of the giant, is dragged. The gas resists its motion, like a swimmer trying to race through thick water. And as the companion is slowed by that resistance, it begins to spiral inward, falling deeper and deeper toward the core of the giant, its orbit decaying in a tightening, quickening spiral. It is worth slowing down here, because this is the engine of the whole story, and it deserves to be felt rather than merely stated. Picture the two stars in the long ages before the catastrophe. They had circled each other, perhaps, for billions of years, a steady gravitational dance, each holding the other in a stable orbit, neither one disturbing the other. This is an utterly ordinary arrangement in our galaxy. Look up at the night sky, at any of the stars scattered across it, and a great many of those points of light are not single stars at all, but pairs or triples or whole families of stars bound together, circling a common center, partners in a dance that can last for the entire lifetime of the cosmos. But the dance is only stable so long as both partners stay the same. And stars do not stay the same. They age, they change. And when the larger of the two began to die, when it swelled into a red giant, the careful balance of the old dance was broken forever. The giant grew and grew, reaching outward across the gap that had always separated the two stars, until at last it touched its partner, and then enclosed it, and the smaller star found itself no longer orbiting in clean, empty space, but ploughing through the thick outer atmosphere of the giant it had circled for so long. From that moment, the smaller star was doomed. There was no escape from inside the envelope. Every time it swept through that resisting gas, it lost a little energy. And losing energy meant falling closer, and falling closer meant ploughing through denser gas still. Losing energy faster, falling faster. The spiral tightened and accelerated, a runaway descent. The companion winding inward toward the core of the giant, in what was, by cosmic standards, a remarkably swift and violent plunge. But the companion does not simply vanish quietly. As it spirals inward, it dumps the enormous energy of its orbit into the gas around it. Think of all the energy bound up in a star's motion as it circles another, the momentum of an entire sun swinging through its orbit. As the companion falls inward, all of that orbital energy is poured into the surrounding envelope of gas, violently, rapidly, like a spoon stirred so hard it flings the contents of the bowl out across the room. And that is what happens. The envelope of the giant, suddenly injected with all the orbital energy of the doomed companion, is blasted outward, flung into space at tremendous speed. Not the gentle exhalation of an ordinary dying star, but a great violent heave, powered by the death spiral of a consumed companion. This is the source of the speed. This is what flung the gas of the Boomerang Nebula outward at 164 kilometers per second. Not the death of one star, but the merger of two. The companion, spiraling in, consumed at last by the core of the giant, gave up the energy of its entire orbit in one catastrophic event, and that energy went screaming outward as a shell of gas moving 10 times faster than any single star could have managed. And that gas, expanding so violently into the surrounding dark, cooled by the unforgiving physics of adiabatic expansion, fell below the temperature of the universe itself. The coldest place we have ever found was made by one of the most violent events a pair of stars can undergo. A stellar merger, the consuming of one star by another. Out of that violence, paradoxically, beautifully, came the deepest cold in the known cosmos. There is one more detail here that gives the whole thing a strange and human poignancy. When astronomers measure how fast the gas is moving and how far it has traveled, they can work backward and estimate when this event occurred. When the companion was consumed, when the great cold shell was first flung outward, the answer is that it happened recently. In cosmic terms, astonishingly recently. The outflow appears to be somewhere between roughly 1,000 and 2,000 years old. Perhaps 1,500 years, give or take. 1,500 years. Set against the 13.8 billion year age of the universe, that is nothing at all. It is the blink of an eye laid against an entire human lifetime, and then some. When this gas was flung from the dying star, when the companion made its final plunge and the great cold was born, human beings were already here. We were building. We had cities and empires and written words. Somewhere on Earth, while this catastrophe unfolded 5,000 light years away, people were living ordinary lives, entirely unaware that the coldest place in the known universe was at that very moment being formed in the constellation of Centaurus. And the light carrying the news of it is only reaching us now. We are, in a sense, watching something that just happened. A fresh wound in the sky, a very young ruin. And to see what that ruin actually looks like in all its delicate and revealing structure, we need to turn at last to the instrument that showed us its true shape. Because when Alma looked closely at the Boomerang Nebula, it did not see a simple round cloud. It saw something far more intricate, something shaped and structured and telling. It saw an hourglass. To understand what the Boomerang Nebula truly is, you have to understand the difference between two ways of seeing. For most of the time that human beings have looked at the sky, we have seen it in visible light. The light our eyes evolved to catch, the same light that lets you see this room around you. And in visible light, the Boomerang Nebula is a soft, ghostly thing. The Hubble Space Telescope photographed it this way, and the image is genuinely beautiful. Two faint lobes of pale light leaning away from a central point, like the wings of some delicate insect, or the gentle double curve that gave the nebula its name. A bow tie of light against the black. But here is the important thing to understand. When Hubble photographed those glowing lobes, it was not seeing the gas itself glowing. The gas of the Boomerang Nebula is far too cold to glow on its own. What Hubble saw was starlight. Light from the central star, scattering off the countless tiny grains of dust suspended in the nebula, the way a car's headlights catch the drifting particles of fog. The visible shape of the Boomerang Nebula is a shape painted in reflected light. It shows you where the dust is, lit up by the star at the center, but it does not show you the cold gas, and it does not show you the deeper structure hidden within. This is a distinction worth holding on to, because it changes how you understand every beautiful image of space you have ever seen. We tend to assume that a photograph of a nebula shows us the thing as it really is, the way a photograph of a mountain shows us the mountain. But what a telescope captures depends entirely on what kind of light it is built to gather. And different kinds of light reveal entirely different things about the same object. The visible light image of the Boomerang Nebula and the sub-millimeter image are both true, and yet they show almost completely different things. One shows the dust-catching starlight, the other shows the cold gas and its hidden architecture. Neither is the whole object. Each is one layer, one way of seeing, one slice of a reality too rich for any single instrument to capture all at once. To truly know an object in space, we have to look at it again and again, through every kind of eye we can build, and assemble the full picture from all of them together. To see the deeper truth, you need different eyes. You need to see not in visible light, but in the much longer waves of sub-millimeter radiation, the kind of light that cold molecules themselves emit and absorb. And to see it sharply, in fine detail, you need an instrument of extraordinary power. That instrument is ALMA, the Atacama Large Millimeter Array. It sits more than 5,000 meters up on a high plateau in the Chilean Andes, in one of the driest places on Earth, because water vapor in the air would blur the faint signals it is built to detect. It is not a single telescope, but a great array of dishes, dozens of them, spread across the desert and linked together so that they act, in effect, as one enormous eye. By combining their signals, ALMA can see the cold gas of the cosmos with a clarity that no single telescope could ever achieve. The location alone tells you something about how difficult this kind of seeing is. The plateau where ALMA sits, called the Chajnantor Plateau, is so high that the air is thin enough to leave visitors short of breath, and so dry that almost no rain ever falls there. These harsh conditions are not an accident or an inconvenience to be endured. They are the entire point. The faint submillimeter light that ALMA gathers is easily absorbed by water vapor in the atmosphere. Down at sea level, beneath the full thickness of our moist air, this light from the cold cosmos would never reach the ground at all. So the telescopes were carried up to one of the highest, driest places that human beings can practically work, above as much of the obscuring water as possible, to catch a kind of light that almost never makes it down to where we live. There is a quiet poetry in that. To see the coldest, faintest gas in the universe, we had to climb nearly as far out of our own atmosphere as we could manage while still standing on the Earth. And what ALMA gathers is a kind of light that tells a different story than the light our eyes can see. Cold molecular gas, the gas that fills the dark places between and around the stars, does not shine in visible light. It is too cold for that. But it does emit and absorb light at these longer, submillimeter wavelengths, in patterns as distinctive as fingerprints. Each kind of molecule has its own signature in this light, its own particular frequencies at which it speaks. So when ALMA looks at a cold cloud, it does not merely see a vague glow. It can read the cloud. It can tell which molecules are present, how they are arranged, how fast they are moving, and in which directions, how dense and how cold they are in each separate region. It turns a faint and invisible cloud into a detailed, three-dimensional map of motion and temperature and structure. It lets us see, in effect, the cold itself. When ALMA turned this vast and patient eye upon the Boomerang Nebula, it saw past the pretty bow tie of reflected starlight that Hubble had captured. It saw the cold gas itself, and the shape of that gas was not the simple double lobe of the visible image. It was an hourglass, two great cones of gas meeting at a narrow waist in the middle, flaring outward in opposite directions like the two chambers of an hourglass with the sand running between them. This was the true structure of the outflow, hidden beneath the softer glow that visible light had shown. A precise, symmetrical, double-coned shape, sculpted by the violence of the stellar merger and the geometry of the system that produced it. And the scale of this hourglass is difficult to hold in the mind. The hourglass structure stretches some 21,000 astronomical units from one end to the other. An astronomical unit is the distance from the Earth to the Sun, about 93 million miles. So 21,000 of them, laid end to end, is a distance so vast that light itself takes months to cross it. But the hourglass is not even the whole of it. ALMA revealed that this inner hourglass is embedded inside a larger, rounder, outer envelope of ultra-cold gas. And that outer envelope extends to something like 120,000 astronomical units across, more than a full light year. A sphere of frigid gas larger than the distance from our sun to its nearest stellar neighbors, all of it colder than the background of the universe, all of it produced by the death of a single pair of stars. At the center of the hourglass, at the narrow waist where the two cones meet, ALMA found something significant. A dense ring of dust and gas, thicker and more concentrated than the rest. This waist, this central band, is understood to be the remnant of the orbital plane of the original binary system. It is the leftover disk of material that gathered around the equator of the dying stars, in the plane where the companion once orbited before it spiraled inward to its end. And this dense central ring does something important. It acts as a kind of nozzle, a collimator. As the gas was flung outward from the dying star, this thick equatorial band blocked it from escaping sideways around the middle. The gas could not push easily through the dense ring at the waist. So instead, it was funneled, channeled, squeezed out along the two open directions, up and down, away from the plane of the ring. That is why the nebula takes the shape of an hourglass, rather than a simple expanding sphere. The dense ring at the center pinched the outflow into two opposing cones, like a hand squeezing the middle of a balloon and forcing the air to bulge out at both ends. So the shape itself is a record. It is a frozen account of how the gas was ejected and how it was channeled. The hourglass is not a still, finished sculpture. It is a single frame of an ongoing event, a snapshot of gas still racing outward at 164 kilometers per second, still expanding, still being shaped by the dense ring it left behind. If you could watch it across thousands of years, you would see the hourglass slowly growing, the cones lengthening, the whole structure swelling outward into the dark. We are seeing a moment, a held breath, the shape of a catastrophe still in motion. The hourglass is beautiful, but it is more than beautiful. Its shape is a map, and if you read that map carefully, it tells you something remarkable about where the cold actually lives within the nebula. Because the cold, it turns out, is not spread evenly. The Boomerang Nebula is colder in some places than in others, and the pattern of that cold reveals the physics that made it. Think back to the principle at the center of everything: adiabatic expansion. Gas cools when it expands, and it cools most deeply when it expands fastest and most freely. Now look at the hourglass again, with that principle in mind. The gas is not all moving the same way. At the dense waist in the middle, where the equatorial ring sits, the gas is more crowded, more confined, warmer, and denser. It could not expand as freely, hemmed in by all that surrounding material. But out along the two cones, along the open axis where the gas was funneled and flung outward with the most violence, the gas had room to race outward into the emptiness. It expanded the fastest. It spread out the most freely. And so, by the unforgiving logic of adiabatic cooling, it cooled the deepest. The coldest gas in the Boomerang Nebula is not at the center where the dying star sits. The very heart of the nebula, near the star, is actually somewhat warmer. The deepest cold is found out in the expanding lobes, out along the flaring cones of the hourglass, where the gas has done the most expansion work, where it has rushed outward the farthest and the fastest from the place it began. There is something quietly profound in that. The coldest place in the universe is coldest not at its core, but at its expanding edges. The cold is a product of motion, of the headlong outward rush, and so it is deepest where that rush has carried the gas farthest from home. The chill lives in the flight, not in the center, and there is a further strangeness worth sitting with. We tend to imagine the coldest places as the stillest places, the most quiet and motionless. A frozen winter night feels still. The deep cold of an empty room at the dead of night feels like the absence of all motion and all activity. But the cold of the Boomerang Nebula is exactly the opposite. It is a cold born entirely of violent, headlong motion. The gas is not still at all. It is racing outward at 100 miles every second, faster than any rifle bullet, faster than nearly anything in the ordinary universe. And it is precisely this furious motion, this relentless outward rush, that makes it so cold. The stillness we associate with cold is here replaced by its opposite. This is the coldest place we know, and it is also one of the most violently moving. The two facts are not in tension. The one creates the other. The motion is the cold. The nebula may not have finished cooling. The gas is still expanding. It is still racing outward at that tremendous speed, still doing the work that makes it cold. As long as the expansion continues unchecked, the deepest reaches of the nebula may grow colder still. The record-holding cold of the Boomerang Nebula might not yet have reached its lowest point. The coldest moment of the coldest place in the universe may still be ahead of it, somewhere in the next stretch of its brief and frigid existence. But that existence is brief, and that brevity is the next part of the story, and perhaps the most poignant part of all. Nothing about the Boomerang Nebula is permanent, least of all its record. The coldest place in the universe holds its title only for a little while. The very same process that created it, the death of the central star, is also the process that will, before long, destroy the cold and erase the anomaly. The Boomerang Nebula is a fleeting thing. We happen to be alive at the brief moment when it can be seen for what it is, and that is a piece of remarkable good fortune. To understand why it cannot last, recall where the central star is in its life. It is in the pre-planetary nebula phase, that narrow window between the red giant and the final unveiling. The star has cast off its outer layers, and they are expanding outward as the great cold cloud. But the exposed core of the star is still contracting, and as it contracts, it is heating up. Slowly, steadily, the central star is growing hotter. For now, it is only 6,000 or 7,000 degrees at its surface, warm but not fierce, not yet hot enough to light up the surrounding gas. But it will not stay that way. As the core continues to contract, its temperature will climb, and eventually it will reach a threshold, somewhere around 30,000 degrees, where it begins to pour out intense ultraviolet light. When that happens, everything changes. That flood of ultraviolet light will strike the surrounding gas and energize it, ionize it, set it glowing from within. The cold, dark, expanding shroud will become a luminous, glowing cloud. The pre-planetary nebula will become a true planetary nebula, one of those gorgeous, intricate, glowing shells of gas that fill so many famous astronomical images. It will be beautiful, and it will be warm. The glow is warmth. To light up the gas is to heat it. The moment the central star becomes hot enough to ignite its surroundings, the great cold of the Boomerang Nebula will begin to lift. The temperature will climb. The shadow it casts against the background of the universe will fade and then vanish. The nebula will cease to be colder than the cosmos. It will become just another glowing planetary nebula among the many, lovely but ordinary, its record surrendered. And there are already hints that the warming has begun. When astronomers studied the ALMA data closely, they found signs that the outermost fringes of the nebula are no longer quite as cold as the inner regions. The edges appear to be warming gradually, perhaps as they encounter the faint warmth of the surrounding interstellar space, perhaps as the dynamics of the expansion slowly shift. The deepest cold still reigns in the heart of the hourglass lobes, but at the margins, the thaw may already be creeping in. How long does the Boomerang Nebula have? Not long. Perhaps a few thousand years more before the central star crosses its threshold, and the great warming begins in earnest. A few thousand years sounds like a long time to us, whose civilizations are measured in centuries and whose lives are measured in decades. But against the life of a star, against the age of the universe, it is the merest flicker. The Boomerang Nebula has been the coldest place in the universe for only about 1,500 years, and it may hold the title for only a few thousand more. a window of a few thousand years, in a universe nearly 14 billion years old, and we are here for it. Of all the moments we might have looked, of all the eras of cosmic history in which conscious beings might have turned their instruments toward the constellation of Centaurus, we are looking now, during the brief flicker when the coldest known place in the universe exists to be found. A few thousand years earlier, and the companion star had not yet been consumed, the great cold not yet born. A few thousand years later, and the central star will have lit its shroud ablaze, the anomaly gone, the record erased. Think of how narrow that window truly is. The universe is nearly 14 billion years old. Human civilization, with the instruments capable of detecting this cold, has existed for only the last few decades of that immense span. And the Boomerang Nebula has been and will be in its record-setting cold state for only a few thousand years out of those 14 billion. For these two impossibly narrow windows to overlap, for us to have developed the ability to see it during the exact brief moment it exists to be seen, is a coincidence of timing so improbable that it is worth genuine wonder. But there is a flip side to that thought, and it is worth holding too. If the timing is so improbable, then the fact that we found this one at all suggests there must be others. Not others we can see right now, necessarily, but others scattered across the history of the galaxy, each appearing for its own brief window, and then fading. The cosmic freezer is not a single freak event, but a recurring kind of moment, and we happen to have caught one of them in the act. We will return to that idea later, because it changes how we should think about the whole phenomenon. For now, it is enough to feel the strangeness of the coincidence that let us see this particular one. There is a kind of tenderness in all of this. The coldest thing we have ever found is also one of the most fleeting, and it is already beginning to change even as we study it. Its outer fringes are warming. Its central star is heating toward the day it will set the whole shroud glowing. What we are looking at is not a permanent feature of the cosmos, but a passing moment in the death of a star, and we have arrived, by sheer chance, at exactly the right moment to witness it. Before long, it will become ordinary again, and then it will be gone entirely, its gas dispersed into the wider galaxy, the dying star at its center shrunk to a slowly cooling ember. And now, having traveled to it, having understood how it was made and how it is shaped and how briefly it will last, it is time to pull back once more, to leave the nebula behind and rise to a higher view. Because the Boomerang Nebula raises a question larger than itself. It forces us to ask what cold really is, what temperature really means, what the lowest possible temperature even is, and why the universe has a floor at all. To understand why the Boomerang Nebula is so astonishing, we have to understand the nature of cold itself. We talk about cold so casually. A cold morning, a cold drink, a cold wind off the water. But what is cold, really? What is temperature when you strip away the everyday feeling of it and ask what is actually happening? The answer is motion. Everything around you, everything you can see and touch, is made of atoms. And those atoms are never still. They jiggle, they vibrate. In a solid, they tremble in place, locked into their positions but quivering endlessly. In a liquid or a gas, they move more freely, sliding and colliding and flying past one another. This restless, ceaseless motion is the deepest meaning of temperature. Temperature is, in essence, a measure of how vigorously the atoms of a thing are moving. When something is hot, its atoms are moving fast, jostling and colliding with great energy. When something is cold, its atoms are moving slowly, their motion dampened, their energy low. To warm something is to make its atoms move faster. To cool something is to make its atoms move slower. Heat is motion, and cold is stillness, all the way down to the smallest scale there is. And this immediately suggests a profound question. If cold is the slowing of atomic motion, then what happens if you slow that motion all the way down? What if you took something and cooled it, draining away its heat, slowing its atoms further and further until at last the motion stopped entirely? That point, the point at which all atomic motion ceases, is the coldest temperature that can possibly exist. It is the absolute bottom, the floor beneath all floors. There is no colder because there is no slower than stopped. We call it absolute zero. In the everyday units of the Celsius scale, absolute zero sits at minus 273.15 degrees. On the scale that scientists use to measure these depths, the Kelvin scale, which begins counting from this absolute bottom, it is simply zero. 0 Kelvin, the place where motion ends and temperature can fall no further. But here is one of the most elegant and surprising truths in all of physics. You cannot actually get there. Absolute zero can be approached, but it can never be reached. Not by any amount of effort, not with any conceivable machine, not in all the time the universe has left. This is not a limitation of our technology. It is a law of nature, woven into the fabric of how reality works, known as the third law of thermodynamics. Why can it never be reached? Part of the answer lies in the strange rules of the quantum world. Even if you could drain away nearly all the energy of motion from an atom, the deepest laws of physics forbid it from ever becoming perfectly, completely still. There remains always a faint, irreducible flicker of motion, a last trembling that cannot be removed, a whisper of energy that quantum mechanics will not allow you to silence. You can get achingly, vanishingly close to absolute zero. You can come within a hair's breadth. But that final step, the step to perfect stillness, is forever forbidden. There is a beautiful way to think about why the very last step is impossible. Cooling something means removing its heat, carrying its energy away somewhere else. But to carry heat away, you need somewhere colder for it to go, the way water only flows downhill if there is a lower place for it to reach. As you approach absolute zero, the thing you are trying to cool becomes colder than almost everything around it. And finding somewhere still colder to dump its last remaining warmth becomes harder and harder. Each tiny step closer to the bottom requires more effort than the step before, the difficulty rising without limit as you near the floor. The closer you get, the more it costs to go further, until the final approach demands an infinite effort that can never actually be paid. Absolute zero is not so much a wall you crash into as a horizon you can forever approach, but never arrive at, receding before you no matter how far you travel. And yet, we have come remarkably close. The pursuit of absolute zero is one of the great quiet adventures of modern physics. For more than a century, scientists have been inventing ever more ingenious ways to chill matter further and further toward the unreachable bottom. Each new technique opened a new realm of cold, and in each new realm, matter revealed behaviors that had never been seen before. Gases became liquids that had never been liquefied. Some metals, chilled deeply enough, lost all resistance to electricity, letting current flow through them forever without fading, a phenomenon called superconductivity that seems almost magical when first encountered. Some liquids, chilled to the extreme, began to flow without any friction at all, climbing the walls of their containers and creeping out on their own, defying every intuition about how liquids should behave. The deep cold is not an empty, lifeless place. It is a frontier where matter does astonishing and unexpected things, where the familiar rules give way to stranger ones. In laboratories on Earth, physicists have developed astonishing techniques to slow atoms down, to drain away their motion, to chill matter to within a breath of the absolute floor. They use lasers, strange as that sounds. Light, which we think of as a source of heat and energy, can be used with exquisite precision to slow atoms down. The beams are arranged so that an atom moving against them is gently pushed back, again and again, until its motion is reduced almost to nothing. This is called laser cooling. They use magnetic fields to trap and hold the slowest atoms while the faster, warmer ones escape, leaving behind only the coldest. And through these methods and others, physicists have reached temperatures almost unimaginably close to absolute zero, billionths of a degree above it. In some experiments, even closer than that. The idea of cooling something with light deserves a moment because it is so beautifully counterintuitive. We feel sunlight as warmth. We know that light carries energy, that it can heat a surface, that it can even, in great enough concentration, burn. How could light possibly make something colder? The trick lies in the precise nature of how an atom absorbs light. An atom, like a tiny tuning fork, responds most strongly to light of a particular frequency. And by tuning the laser just slightly below that frequency, physicists can arrange things so that an atom only absorbs the light when it is moving toward the beam in a way that nudges it backward, slowing it down. Aim such beams from every direction, and an atom moving any which way is met with a gentle push against its motion, no matter which way it turns. The atom finds itself swimming through a kind of thick syrup made of light, slowed from every side. Its motion bled away photon by photon, until it is nearly, almost, but never quite still. Physicists call this arrangement optical molasses, and the name captures it well. A trap of light that drains the motion, and therefore the warmth, out of matter itself. At these temperatures, something extraordinary happens to matter. As atoms are chilled to within billionths of a degree of absolute zero, they begin to lose their individual identities. They stop behaving like separate particles and begin to merge into a single shared quantum state, a strange new form of matter in which thousands of atoms behave as though they were one. This is called a Bose-Einstein condensate, and it is a phase of matter that does not exist anywhere in the everyday world, that comes into being only at the very edge of absolute cold. Matter, pushed to the brink of perfect stillness, stops being ordinary matter at all. The atoms, no longer jostling and colliding, no longer maintaining their separate selves, settle into a single coordinated whole, a droplet of matter behaving by the strange and beautiful rules of the quantum world, writ large enough almost to see. Now hold all of that in your mind and turn back once more to the Boomerang Nebula. To reach the temperatures we have been describing, billionths of a degree above absolute zero required some of the most sophisticated machinery human beings have ever built. The work of brilliant minds refined over decades, recognized with the highest honors in science. It took lasers and magnetic traps and vacuum chambers and exquisite control, all to chill a tiny sample of atoms in a carefully shielded laboratory. The Boomerang Nebula reached a temperature of about 1 degree above absolute zero on its own, naturally. Out in the wild dark of space, with no laboratory, no lasers, no careful human hand, just a dying star, and the brute physics of violent expansion. A single Kelvin, achieved by nothing more than the death throes of a pair of stars 5,000 light-years away. 1 degree above absolute zero is not as cold as what physicists have achieved in their laboratories. But there is a world of difference between the two accomplishments. The laboratory cold is fragile and tiny and fiercely maintained, a few atoms held at the edge of stillness inside layers of shielding for fractions of a second at enormous effort. The cold of the Boomerang Nebula spans more than a light year. It is a region of frigid gas larger than our entire solar system, larger than the distance to neighboring stars, holding itself colder than the universe with no effort and no machinery at all. Nature built, in the open dark, a freezer the size of a solar system and set it below the temperature of the cosmos, and it did so simply as a consequence of how a certain kind of star happens to die. That is, the scale of the wonder. Not just that it is cold, but that it is cold across such an immensity, achieved so effortlessly by a universe that needed no laboratory to outdo our finest laboratories in sheer reach. But we have not yet faced the deepest strangeness. We have explained how the Boomerang Nebula got so cold. We have not fully reckoned with what it means that it is colder than the background of the universe. To understand that, we have to understand the background itself, the faint, even glow that fills all of space. The thing the Boomerang Nebula is colder than. It is called the cosmic microwave background, and it is the oldest light in the universe. To understand where it came from, we have to go back. Not just thousands of years, not just millions, but all the way back to a time not long after the very beginning. The universe, we have learned, began about 13.8 billion years ago in a state of unimaginable heat and density. And in its earliest moments, it was not the vast, mostly empty, transparent place we see today. It was a dense, blazing fog, so hot and so crowded, light could not get anywhere. The universe was opaque, glowing, impenetrable, like the inside of a star. But the universe was expanding, and as it expanded, it cooled. And about 380,000 years after the beginning, it reached a critical moment. It had cooled just enough, to around 3,000 degrees, for the charged particles to come together into neutral atoms. And suddenly, for the first time, light could travel freely. The fog cleared. The universe became transparent, and the light that had been trapped in that glowing fog was released, set free to stream across space in all directions. That light has been traveling ever since. For 13.8 billion years, it has crossed the expanding cosmos, and it is still arriving, even now, from every direction at once. It is the afterglow of the universe's hot beginning, the released radiance of that first clearing of the fog, and it fills all of space to this very moment. But it has changed along the way. When that light was first set free, it was the glow of a 3,000-degree fog, the color of a dim, red-hot star. Over 13.8 billion years, however, the universe has expanded enormously, and as space itself has stretched, it has stretched the waves of that ancient light along with it. The light has been drawn out, its waves lengthened, its energy diluted, cooled by the very expansion of space across all those billions of years. And so today, that once blazing light has been stretched and cooled until it is no longer visible at all, no longer the glow of a red-hot fog, but a faint hiss of microwave radiation, corresponding to a temperature of just 2.725 degrees above absolute zero. The fire of the early universe, cooled by 13 billion years of cosmic expansion, has become the gentlest possible warmth, a whisper barely above the absolute floor. This is the cosmic microwave background, and it is everywhere. It fills every cubic centimeter of space. Even now, in the room around you, photons from the birth of the universe are passing through a faint rain of ancient light that has been traveling since long before the Earth or the Sun existed. In every small volume of empty space, There are hundreds of these photons, leftover light from the beginning of everything, bathing all of creation in their 2.725 degrees of warmth. There is something worth pausing on in that fact, something that connects this cosmic story directly to your own life in a way you may never have realized. For much of the 20th century, before the days of cable and satellite, television sets received their signal through the air, and when a set was tuned to a channel with no station broadcasting, the screen filled with a restless storm of black and white speckles, and the speakers hissed with random static. That snow, that hiss, was made of many things, stray signals and electronic noise of all kinds. But a small fraction of it, a genuine sliver of that static, was the cosmic microwave background itself. The afterglow of the Big Bang, picked up by an ordinary television antenna, turned into flickering dots on a living room screen. People sat in their homes, half watching the static of an empty channel, unknowingly bathed in light from the birth of the universe. The oldest light there is, falling on the most ordinary of devices. It has always been here, all around us, woven invisibly into the everyday world. And this is why the cosmic microwave background sets the floor. This is why it is the minimum temperature of the universe. Because it is everywhere. Because there is no place you can go to escape it. Anything sitting in the open dark of space is bathed in this radiation, warmed by it, brought up to its temperature. You cannot be colder than your surroundings for long. And in the universe, the surroundings are always everywhere. This 2.725 degree glow, it is the temperature that empty space settles into, the baseline that everything is pulled toward, the coldest that the void itself can be. Or so we thought. Because the Boomerang Nebula sits in this same universe, bathed in this same ancient light, surrounded by this same inescapable glow, and yet it is colder. It has fallen beneath the floor. It absorbs the cosmic microwave background instead of being warmed to its temperature. It drinks in the oldest light in the universe and stays colder than the light it swallows. Let the full weight of that settle here in the quiet. There is a minimum temperature to existence. It was set 13.8 billion years ago in the fire of the early universe, and cooled across all the ages since into the gentle background glow that fills all of space. For 13 billion years it has been the floor, the baseline, the coldest that the open universe is allowed to be. And then, one dying star, in one brief and violent merger, in one small corner of one ordinary galaxy, slipped beneath it, pushed itself for a few thousand years below the temperature of the cosmos itself. It is a small thing in the scale of the universe, a single nebula, a single fleeting anomaly, and yet it is a genuine violation of what we thought the floor of reality was. A place where the universe is impossibly colder than the universe. And here is a thought to carry with you as we prepare to rise to the final and widest view of all. The Boomerang Nebula may not be alone. We found it because it was close enough and bright enough and strange enough to catch our attention. 5,000 light-years is far, but in the scale of the galaxy, it is practically next door. The nebula sits in a direction we could easily study, and its peculiar shape drew the eye of astronomers decades ago, and so we turned our best instruments toward it and discovered its impossible cold. But the process that made it is not unique. The death of a star like this, the consuming of a companion, the violent expansion that drives the great cold, these are not one-of-a-kind events. There may well be other pre-planetary nebulae out there, other dying stars caught in the same brief and violent transition, other ultra-cold outflows quietly absorbing the background light of the universe. A whole hidden class of cosmic freezers scattered through the galaxy, most of them too far or too faint or too obscured for us to have noticed yet. How many might there be? We do not truly know. The Boomerang Nebula is the coldest we have found, and for now, it stands alone in the record books. But it would be a strange kind of arrogance to assume that the one we happen to find is the only one that exists. More likely, it is simply the nearest and clearest example of something the universe does quietly, again and again, wherever the right kind of star dies in the right kind of way. Think of how we found it in the first place. Not because we went looking for the coldest place in the universe, but because a strange little nebula happened to catch the eye of two astronomers in the southern sky, and decades later, someone happened to point the right instrument at it and noticed it was casting a shadow against the ancient light. It was a discovery of attention and luck as much as of intention. The galaxy is vast, and our surveys of it are far from complete, and the kind of cold we are talking about does not announce itself loudly. An ultra-cold cloud does not blaze or flash or call out. It simply sits in the dark, faintly absorbing the background glow, easy to overlook unless you happen to be looking in exactly the right way, with exactly the right instrument, at exactly the brief moment in its life when it is cold enough to notice. So picture them if you like. Out there in the dark between here and the galactic center and beyond, unseen ultra-cold clouds drifting through the void. Pockets of gas colder than the cosmos, casting their faint cold shadows against the ancient light, each one the brief and frozen monument to a pair of stars that came together in violence and produced, against all expectation, the deepest cold in nature. Most of them we will never see. Most of them will form and chill and warm again and disperse, entirely unwitnessed, in the long dark stretches between the stars. And consider what this suggests about the universe itself. We so often think of the cosmos as a place of fire, of blazing stars and searing energy, of heat and light pouring out into the dark, and it is that. But it is also, quietly, a place of profound and active cold. In its dim corners, around its dying stars, the universe is forever making pockets of deep chill, refrigerators built of stellar death, each one slipping briefly beneath the floor that creation laid down. The making of cold is as much a part of the universe's nature as the making of heat. We simply notice the heat more because heat shines and cold does not. But the cold is there, woven through the dark, doing its quiet work wherever a star comes to the right kind of end. The Boomerang Nebula is the one that let us see. The one cold place, near enough and clear enough to teach us that the floor of the universe is not quite as solid as we believed. That, under the right circumstances, in the right brief moment, the cosmos can be colder than its own coldest baseline. And that teaches us something about where everything is going. Because the cold of the Boomerang Nebula, strange and local and fleeting as it is, turns out to be a small preview of the fate of the whole universe. To see why, we have to pull back one final time. Past the nebula, past the constellation, past the galaxy itself, all the way out to the largest view there is. The view of the universe across all of time and the long, slow, cooling road it is traveling toward its end. There is a law that governs everything. It governs the cup of coffee cooling on your table and the stars burning in the sky and the ultimate fate of the entire universe. It is, in many ways, the most relentless and inescapable law in all of physics. It is called the second law of thermodynamics, and its message is simple and quiet and final. Things run down. More precisely, the law says that in any closed system, disorder always increases over time. Physicists call this disorder entropy, And the second law states that the entropy of the universe is always growing, always climbing, never reversing. Ordered, useful, concentrated energy gradually spreads out, disperses, becomes disordered and useless. Hot things cool, differences even out. Structure dissolves. The universe is forever moving from order toward disorder, from concentration toward dispersal, from difference toward sameness. You see this law everywhere, once you know to look for it. A hot cup of coffee always cools to room temperature, never the reverse. It never spontaneously draws heat from the cooler room to make itself hotter. Heat flows from hot to cold. Energy spreads out. Differences fade. A drop of ink in water always disperses into an even gray, never gathers itself back into a concentrated drop. The arrow points always in one direction, toward dispersal, toward evenness, toward the running down of all things. It is worth noticing how deeply this one-way flow is woven into your experience of time itself. Think of all the things that happen in one direction and never the other. A glass falls from a table and shatters on the floor, but shattered glass never leaps back up and reassembles itself into a whole glass on the table. A drop of cream stirred into coffee spreads until the whole cup is an even brown, but a uniform brown coffee never spontaneously separates back into black coffee and a neat swirl of cream. A sandcastle crumbles into a smooth beach, but waves never sculpt smooth sand into a sandcastle. In every case, the direction that actually happens is the direction of increasing disorder, increasing evenness, increasing entropy. So reliable is this one-way flow that some physicists have argued it is the very thing that gives time its direction. The reason we remember the past and not the future, the reason time seems to flow forward and never back, may be nothing more nor less than this relentless increase of entropy, this universal tendency for things to spread out and even themselves down. The arrow of time and the arrow of the second law may be one and the same arrow, and the universe as a whole is subject to this same law. The universe is running down. Right now, we live in an age of tremendous difference, tremendous concentration of energy. There are blazing hot stars and cold empty space between them. There are dense, bright galaxies and vast dark voids. There is structure and contrast and the constant flow of energy from hot places to cold ones. And it is this flow, this difference, that drives everything interesting in the cosmos, including life itself. We are creatures of the difference, sustained by the flow of concentrated energy from the hot sun into the cold of space. But the differences are slowly evening out. The stars are burning through their fuel. Every star that shines is spending a finite store of energy that it can never replace, pouring its heat and light out into the cold dark, where it spreads and disperses and never comes back. The universe is, very slowly, using itself up, and we can trace where this leads. We can follow the arrow of the second law forward, across spans of time so vast that the numbers stop meaning anything and see the shape of the universe's distant future. For now, we are in the age of stars. It is a glorious age, full of light and heat, and the constant birth of new suns, but it will not last forever. The universe is still forming new stars, but more slowly than it once did, the raw material gradually being locked away in stellar remnants or dispersed too thinly to gather. And there will come a time, perhaps 100 trillion years from now, when the last star forms. The final new sun, kindled from the last gathered gas, after which no more will ever be born. 100 trillion years. The universe today is not yet 14 billion years old. 100 trillion is many thousands of times longer than the entire history of the cosmos so far. And that is merely when the last star is born. The longest-lived stars, the small, cool, frugal ones that burn their fuel with miserly slowness, will continue shining for a long time after that, glowing faintly in an increasingly dark and empty sky. But they too will fade. One by one, across unimaginable stretches of time, the stars will exhaust their fuel and go dark. The age of stars will end. The sky everywhere will go black. It is worth lingering on the sheer scale of this future, because the numbers involved are unlike anything in ordinary experience, and there is a strange peace to be found in contemplating them. We are accustomed to thinking of the universe as old. 13.8 billion years is a span so vast that it already defeats the imagination. But against the future that lies ahead, the entire history of the universe so far, from the Big Bang to this very moment, is less than the first heartbeat of a life that will last for ages beyond counting. Consider the eras still to come. We live now in what might be called the Age of Stars, the bright era, when the sky is full of shining suns and the universe blazes with light. This era is young, and it will be long, but it is finite. After perhaps 100 trillion years, when the last star has formed and the longest-lived of the small dim stars have finally guttered out, the bright era ends, and a new and darker era begins. In this next era, the universe is lit only by the fading embers of dead stars, the cooling cores of suns that once shone, glowing ever more faintly as they release the last of their stored warmth into the dark. Dim and dying remnants, drifting through an increasingly empty cosmos, the afterglow of a vanished age of light. This dark era stretches on for spans of time that make the entire bright era look like a brief flash. And through it, slowly, even these last embers cool and dim and finally go dark, until no warmth remains anywhere but the great black holes and the thin, cold haze of scattered particles. And then comes the longest era of all, the era of the black holes, the last structures standing in a universe otherwise emptied of everything. They sit in the dark, these great gravitational wells, the final monuments of a cosmos that once blazed with light. And they endure for spans of time so long that the numbers lose all meaning. The largest black holes will take something like 10 to the power of 100 years to evaporate completely. That is a 1 followed by 100 zeros, a number so vast that it is not really a length of time at all in any sense the human mind can grasp. It is closer to a kind of mathematical eternity. But even that eternity ends. Even the black holes, given enough of this near infinite time, will fade away, evaporating into the faintest dispersal of particles and radiation. And when the last black hole is gone, when the final remnant of structure has dissolved, what is left? What is left is almost nothing. A universe stretched unimaginably vast and thin, filled with a sparse and uniform haze of particles and faint radiation, drifting in the dark. No stars, no galaxies, no structure of any kind, no differences left anywhere, no hot places and cold places, no flow of energy from one to another, just an even, featureless, silent sameness spread across a space grown so enormous that the few remaining particles drift unthinkably far apart. And the temperature of this final universe? It falls and falls, forever approaching that absolute floor we spoke of, the absolute zero that can never quite be reached. The universe in its final state grows ever colder, asymptotically, drawing nearer and nearer to absolute zero across spans of time without end, never quite arriving, but coming forever closer to perfect, motionless cold. Physicists have a name for this distant fate. They call it the heat death of the universe. It is a slightly misleading name because there is no heat in it at all. It would be truer to call it the cold death. The universe does not end in fire. It does not end in a great final explosion or a dramatic collapse. It ends in cold, in stillness, in an endless, even, silent dark growing colder forever, as all the energy that ever was spreads itself so thin and so evenly that nothing can ever happen again. The universe does not end in a bang. It ends in a long, slow, deepening cold. And now, at last, we can see the Boomerang Nebula for what it truly is. We have called it a violation, an anomaly, a place that should not exist, colder than the floor the universe laid down at the beginning. And in the here and now, in the age of stars, that is exactly what it is. In a cosmos full of heat and light and difference, the Boomerang Nebula stands out as a strange exception, a pocket of cold deeper than its surroundings, an oddity to be marveled at. But seen against the whole long arc of cosmic time, the Boomerang Nebula is not an exception at all. It is a preview. It is a small, early glimpse of where everything is going. The coldest natural place we have ever found is a tiny foretaste of the fate that awaits the entire universe. That deep, deep cold, colder than the background glow, is the direction the whole cosmos's traveling is traveling given enough time. The Boomerang Nebula has simply arrived there early. It is a small region of space that has, through the particular accident of how its star died, reached ahead of schedule the kind of cold that all of space will one day know. Consider what that means for how we see ourselves and everything around us. Everything that burns is temporary. Every star, including our sun, is a brief flame against the encroaching dark, a passing concentration of energy that will, in time, spread out and fade. Every galaxy is a temporary gathering. Every warm thing, every bright thing, every living thing is a local, fleeting deviation from the universe's deep and patient trend toward cold and stillness and even silent sameness. We are the exceptions. The heat and the light and the life are the anomalies. The cold is the rule. Sit with that for a moment because it reframes everything. We tend to think of warmth and light as the natural state of things, and cold and dark as their absence, the gaps where the warmth has not yet reached. But the truth, across the whole sweep of cosmic time, is the other way around. Cold and dark and stillness are the natural state, the baseline, the destination toward which everything flows. Warmth and light are the rare and temporary exceptions, brief deviations carved out for a while by the slow burning of the stars. We live inside one of those exceptions. Our entire world, our entire experience, every warm morning and every bright afternoon, every living thing that has ever drawn breath, exists within a brief and precious bubble of warmth in a cosmos that is, by its deepest nature, cold and growing colder. The warmth is not the rule that the cold interrupts. The cold or off-flim. The cold is the rule, and the warmth is the brief and beautiful interruption. And the Boomerang Nebula is a place where the interruption has, locally, already ended. Where the deep cold has reasserted itself ahead of schedule. It is a small piece of the cosmic baseline, the universe's true and final nature, showing through early in one cold cloud, while all around it the warm era still blazes on. We live in the warm era, the age of stars, and it feels permanent to us because our lives are so short against it, because the stars have shone for all of human history and will shine for all of human history yet to come. But it is not permanent. It is a phase, a bright, brief, glorious phase in a story that stretches almost endlessly beyond it into the dark and the cold. And so the Boomerang Nebula, that strange cold cloud in the constellation of Centaurus, is not really an oddity standing apart from the universe. It is the universe showing us something true about itself, showing us, in one small place and one brief moment, what it has been quietly trending towards since the first instant after the beginning. The cold that the Boomerang Nebula reached through the violence of a stellar merger is the same cold that the whole cosmos will reach, far more slowly and far more completely in the unimaginable depths of its future. The coldest place in the universe is not a violation of the universe's nature. It is a glimpse of the universe's destiny. So let us return one last time to that cold cloud 5,000 light years away. Let the wider view fall away and come back to rest on the thing itself. There it is, the ghostly lobes of the hourglass, faintly glowing where the central star's light catches the dust, the deeper, colder gas spreading invisibly beyond, more than a light year across, holding itself below the temperature of the universe. And at the very center, the dying star, a single contracting ember, slowly heating toward the day when it will light its shroud ablaze and the great cold will begin to lift. For now, though, the cold endures. Right now, as you rest here, there is a place in the sky where the universe has already begun its long cooling. A small region of space that has reached ahead into the deep cold of the far future and waits there quietly in the constellation of Centaurus. A pocket of the end formed early, drifting in the dark. The heat death of the universe is unimaginably distant. It lies beyond spans of time that make the entire history of the cosmos look like a single morning. We will not see it. Nothing we know or love will see it. It belongs to a future so remote that it can barely be called a future at all. And yet it has already begun, not everywhere, not all at once, but in one place, in one cold cloud around one dying star, the long cooling has already started. The universe has shown us its ending in advance, written small in gas and dust, 5,000 light years away. It is worth holding both of these truths at once, here in the stillness, because together they say something gentle about our place in things. On the one hand, we are tiny and brief. Our lives are the merest flicker against the vast cooling of the cosmos, and the heat death lies so far beyond us that we cannot even properly imagine the gulf of time between here and there. On the other hand, we are the ones who get to know all of this. We are the brief, warm creatures who, in our short flicker of existence, have managed to look out across 5,000 light years to find the coldest place in the universe, to understand how it was made and why it is so cold, and what it tells us about the deep future of everything. The cosmos is busy cooling, slowly and without any awareness of itself, toward its silent end. And in one small corner of it, for one brief moment, it produced beings who could look up and comprehend the whole long story. There is something quietly remarkable in that. The universe is winding down, and yet it paused in us to understand its own winding down. So there is no need for the cold to frighten us. The heat death is real, and it is coming. But it is coming on a timescale that has nothing to do with us, nothing to do with our lives or our world, or even the long future of the star that warms us. What we have, instead, is the warm era, the age of light, the brief and glorious window in which stars shine and worlds turn and warmth flows and on at least one small world, beings have arisen who can look out at the coldest place in the universe and feel not dread, but wonder. The great cold is coming for everything, in time. The stars will fade, the galaxies will dim, the black holes will evaporate, and the cosmos will settle at last into its endless, even, silent dark. But that is for the deep future, far beyond all reckoning. Tonight, there is only this: a quiet wonder, a strange and beautiful cloud, colder than the universe that holds it, glowing softly in the dark of the southern sky. A reminder that the cosmos is stranger and more delicate than we imagine, that it keeps secrets in its quietest corners, and that even its coldest, emptiest places have a story worth telling. The heat death has already started. It just started in one place first. Rest well.